Physics chapter 26 theory video 3 magnetic flux and magnetic flux linkage is what we are talking about. So you have understood what magnetic flux density is. So now this electromagnetic induction, how it is related and how the electrical field and the magnetic field, how they interfere is what we have figured out so far. Now how are we going to get the value of this EMF that has been generated as a result is what we are going to figure out using the equation. We know that magnetic flux density was defined as F upon IL. Now we are going to define the magnetic flux as a quantity. So what we do is we have to imagine the magnetic flux density to be the number of magnetic field lines passing through a particular area through that region. Magnetic flux is the total number of magnetic field lines passing a particular area, a cross-sectional area. Then this particular area, if we take it as A, the magnetic field normal to A, we mark it as the magnetic flux phi, phi phi. So that must be equal to the product of magnetic flux density and the area. Magnetic flux density into area will give us the magnetic flux of phi. So this is what we are trying to figure out. So here B is there, that is the magnetic flux density. That multiplied by the area will give you the magnetic flux. So if it is normal to the area, that is if it makes a 90-degree angle, when the field is normal to the area. However, if the magnetic magnetic flux is at an angle, if it is not normal, right? If it is at a theta angle to flux, what will happen? We'll have to take theta also into consideration. So if it is perpendicular, phi equals BA. If it is not perpendicular to the plane of the cross-sectional area, then we have to take the theta angle between normal to area to get B cos theta. So then we have to use this equation. So this is normal is the 90-degree line. So that is the angle that you need to consider. Once again, please remember that as well. So the normal is this. Normal is this. This is the normal line. That is a 90-degree line. I hope you understand that. Now, moving on, we know that if now the equations that we have got are magnetic flux phi equals B cos theta into A, or else BA cos theta. It's the same thing because everything is multiplication. When theta is equal to 90, phi becomes 0. When theta equals 0, phi equals BA. That is, theta in this particular situation, like I explained earlier, theta is the angle between the normal and this. This is theta. Right? So theta is 90 means at this point, when the magnetic field line is coming like this, then phi is going to be 0. If it is 90, then if the field lines are also like this along with the normal, then what happens is it is simply equal to BA, because we don't have to consider any thetas in at that point. There is no angle in between. So if there is a coil with n turns, we speak about something called magnetic flux linkage. This linkage is the product of the magnetic flux and the number of turns. So magnetic flux linkage is equal to n phi or BAN cos theta. BAN cos theta. I hope that makes sense. So phi is calculated by BA cos theta. Magnetic flux linkage is calculated by n phi. So we replace phi with the equation. So it becomes BAN cos theta. The unit for a magnetic flux and the magnetic flux linkage is the Weber, WB. 1 Weber is the magnetic flux that passes perpendicularly through a cross section of area 1 meter squared when the magnetic flux density is 1 T. 1 T. So 1 Weber is equal to 1 Tm squared. 1 Weber is equal to 1 Tm squared. So then an EMF is said to be induced whenever there is a magnetic flux link in the circuit changes with respect to time. So along with time, if the magnetic flux changes, then there is a EMF being induced. Because magnetic flux is equal to BA cos theta, we can have 3 different ways EMF can be induced. Because BA cos theta, we can change B, we can change A, we can change cos theta. That is, the magnetic flux density can be changed, cross-sectional area can be changed, and angle can be changed. So let's look at this example to better understand what they have spoken about. Figure 26.13. So this is this diagram. So there is a coil, and then there is a field running through it. Shows a solenoid with a cross-sectional area of 0.1 meter squared. It is linked by a magnetic field of flux density 2 × 10⁻³ Tesla and has 250 turns. Determine the magnetic flux and flux linkage for this solenoid. So we have the equation to figure out magnetic flux and flux linkage. We know magnetic flux, we calculated magnetic flux, phi is equal to BA cos theta, right? So here we have B to be a certain value, T to be a certain value, and theta is, in this particular situation, theta is 0. Theta is 0, angle theta is 0, and N is 250 turns. So flux is phi BA when theta is 0, because it is parallel. It is actually goes through it falls through at a 90-degree line. It falls at a 90-degree line. Then phi is BA 2 × 10⁻³ into 0.1, 2 × 10⁻⁴ Weber. So flux linkage is N phi. Then once again we get 5 × 10⁻² Weber. So magnetic flux linkage and magnetic flux both have the same units. So that is something that you need to understand. So here the cross-sectional area is what you need to take into consideration. You might get confused as to how the 90-degree comes. So this cross-sectional area is what we refer to. So the line comes like this. So it is at right angles to the cross-sectional area. So that is why we take theta to be 0. I hope that makes sense to you. Right. So now we did the calculation. If you have understood, you have to do the question number 4, 5, 6, 7, 8 and 9, of course. So do all of those questions, but let me first give you a note so that you can understand it better. So I gave you a little bit of more explanation than the earlier video, but if you need further explanation, please tell me, then I will give you more details. And in the notes also I will give you a little bit more than what they have mentioned here. So the most important thing that you remember is how the relationship develops in comparison to earlier lessons. So the only change that they have introduced to the final paper is that they relate, unlike the earlier situations, they relate different lessons into the same question. This was not something that happened previously, but they have now changed it in such a way that it is the similar sets are given in the same question. So that would make it easier for you to answer the questions. It would be easier, but you have to remember all of those things and how they are linked. So they are not going to give questions that would directly ask you something out of the blue, but they would rather ask you. There would be a certain development that you would be able to understand. So using that development, you will be able to answer the questions easily. Write down. Magnetic flux density was defined by the equation B equals F upon IL. When this magnetic flux density is pictured as the number of magnetic field lines passing through a region per unit area, we can get an understanding for magnetic flux. Put a dash and write down. Total number of magnetic field lines passing through a cross-sectional area A. Leave a line and write. Magnetic flux phi, it is written like this. You generally add these two symbols. So it's like an I across O, something like this. The magnetic flux phi is equal to the product of magnetic flux density into area. Product of magnetic flux density and area if the field lines are normal to the area. That is, if the field lines fall at right angles to the area. If it is at an angle, we would have to consider that angle as well. So please draw this diagram and then write if theta within brackets write theta is the angle between normal and the field line. Close brackets and write if theta is 0, then magnetic flux phi equals BA. If it is not perpendicular to the plane of the area, then magnetic flux equals B cos theta into A or BA cos theta. Magnetic flux phi equals BA cos theta. For a coil of n turns, leave a line and write, for a coil with n turns, magnetic flux linkage is the product of the magnetic flux and the number of turns. Right. So now how they can actually give you questions is by the new method. How they can give you questions is by relating. Now in the earlier situations when they took a certain part, there was no development from one question to the next. But here they would give you, the first part would be from electricity, and they would talk about the solenoid and how the voltage is developed in that. And then from the same question, from the same diagram, they will give you, without giving a separate question, for magnetic flux or flux density, they will give you the same in the same question they will develop this. So you'll have to take the same values, and it is easier because you have already all of these things, all the details are already registered in your mind. Then write down magnetic flux linkage is the product of the magnetic flux and the number of turns in the coil, n into phi, or BAN cos theta. So you have to remember, if it is at right angles with the normal, then it is simply BAN, magnetic flux linkage. Magnetic flux and magnetic flux linkage are both measured in Weber, capital W, simple B. Then define one Weber. 1 Weber is the magnetic flux that passes through a cross-sectional, that passes perpendicularly through a cross-section of area 1 meter squared when the magnetic flux density is 1T. Therefore, 1 Weber, 1 WB is equal to 1 Tm squared. From the equation magnetic flux linkage equals BAN cos theta, and magnetic flux equals BA cos theta, we can understand that there are three ways an EMF can be induced. When you consider N, we can actually, there are four ways that we can increase the EMF, but here we are talking about how it can be changed. First, we change B, that is changing the magnetic flux density B, then 2, changing the cross-sectional area A of the circuit, then change the angle theta. So I hope you understood. If you understood, please do the questions 4 to 9, and in the next video we will discuss Faraday's law of electromagnetic induction.